this video, we're going to determine whether this line 2x plus 3y equals 1 is a subspace of R2. So there's a couple things we need to check. We need to check to make sure it's non-empty. All we have to do is exhibit a single point that we know is on this line. And then we have to check closure under the two operations. So I'm choosing the point -1, 1, and if I plug it into 2x plus 3y equals 1, it does satisfy that equation. So it's definitely on the line, so the set is non-empty. Now closure, there's two operations we need to check. We need to check the vector addition operation in R2 and the scalar multiplication operation. To prove that it's closed under the vector addition, we would have to use arbitrary points on the line. So x1, y1, and x2, y2, and show that no matter what those numbers are, no matter what those ordered pairs are, when we add them together, we get another ordered pair that has to be on that line. But to show that it's not closed, we just have to exhibit two specific points that lie on the line, but their sum does not lie on the line. I am going to choose -1, 1, and 1/2, 0. Both of those points lie on that line. You can check by just plugging the ordered pairs in. But when I add them together, I get the ordered pair -1/2, 1. And if I try to plug that into the equation, 2 times -1/2 plus 3 times 1, I get 2. I don't get 1. So the sum is not on that line, so that means it's not closed under scalar addition because I found two specific points whose sum is not on the line. I've just proven that it's not a subspace. I don't need to check scalar multiplication, but let's just check it anyway. I'm going to show that if I take the point -1, 1, which does lie on that line, and I multiply it by 2, I get something not on that line. So I get the point -2, 2. When I try to plug that into the equation, I don't get 1, I get 2. So it's not closed under either operation. So this line L is not a subspace of R2. So what kinds of lines are subspaces of R2? We saw that this line 2x plus 3y equals 1 is not a subspace of R2. Let's check a similar line. Let's check 2x plus 3y equals 0. So first of all, we know it's non-empty because we can find a point that lies on that line. The point -3, 2 satisfies the equation. So we know it's non-empty. Now, we're going to check closure under two operations. To check closure under addition, to show that it is closed under addition, I need to show that when I add two arbitrary points that satisfy that equation, the sum will satisfy that equation. So I'm going to take that equation and I'm first going to solve it for y in terms of x so I can get the relationship. So y is equal to -2/3 x. So now an arbitrary point on the line has to look like this. x1, -2/3 x1. So the second coordinate has to be -2/3 times the first coordinate. So let's take 2 points that look like that. So x1, -2/3 x1 is 1 point, and then x2, -2/3 x2 is another point on that line. So when I add those 2 points together, I get the point x1 plus x2, -2/3 x1 plus -2/3 x2, and I can rewrite that second coordinate as -2/3 times x1 plus x2. And now we can see our first coordinate is x1 plus x2, and our second coordinate is -2/3 times the first coordinate. So that satisfies the equation. So this line is closed under addition. So let's check closure under scalar multiplication the same way. So if I take any point, arbitrary point, that satisfies the equation, and I multiply it by an arbitrary scalar, c, the first coordinate is c times x1, the second coordinate is c times negative 2/3 x1, and I can rewrite that second coordinate, negative 2/3 times c times x1. So we can see that the second coordinate is negative 2/3 times the first coordinate. So this has to lie on that line. It satisfies the same equation. So it's closed under scalar multiplication. So it turns out that this line, 2x plus 3y equals 0, is a subspace of R2. The equation is very similar to the equation of the other line. The only difference was that number on the right side. So let's look at all the subspaces of R2. It turns out the only subspaces of R2 are the trivial subspace. It's the set that just contains the origin, the point 0, 0. That's a subspace, and it's called the trivial subspace. And any line that goes through the origin, any line that contains the point 0, 0 turns out to be a subspace. So if you have a line in R2 that does not go through the origin, it's not going to be a subspace. And then R2 is a subspace of itself. So those are the only three possible subspaces of R2. And similarly, in R3, the only subspaces that we have are the trivial subspace, the set that just contains the origin in R3, any line in R3 that contains the origin, and then any plane in R3 that contains the origin, and of course R3 itself. All right, you will get some practice describing geometrically various subspaces of R2 and R3, and I'll see you in another video.